Hi everyone. Today we're going to be talking about two topics. One is going to be the T confidence intervals, and the other being t-test. One sample, and two sample. So this T here, what this T stands for is it comes from what's called the T distribution. And sometimes you'll see this called students T distribution. And this is a distribution that's very similar to the normal distribution. Remember, the normal distribution was symmetric and bell-shaped, kind of like that. And a T distribution is very similar in the fact that it is symmetric and bell-shaped. The difference being is that the T distribution changes its shape according to your sample size. So as the size of your sample gets larger and larger, your T distribution becomes closer and closer to a normal distribution. So if this here was a normal distribution, then something a T distribution could look like is maybe something like this. And then maybe if your sample size increases, it starts to look like this with a larger sample until you get a big enough sample that it becomes, basically like a normal distribution. Normal distributions we use to describe population, the distribution of a population. T distribution is used to describe a sample. So you take a sample, and from the sample, you can get the sample mean, the sample standard deviation, and then the sample size. And again, your mean is what this is centered on, but the shape is going to change depending on your sample size. As it gets larger and larger, it'll get closer and closer to a normal distribution. But you still describe the distribution with a mean and standard deviation. You just also have a sample size. A normal distribution does not assume a sample size. It's assuming a population with a very, very, very large sample size, so large that what the actual size is does not actually matter or do anything for the analysis. But with a T distribution, your sample size matters, and as your sample size gets larger and larger, it becomes more like a normal distribution. A general rule of thumb is we like to see the sample size bigger than 30 to be considered something that looks like a normal distribution, but t-tests can certainly be used for sample sizes below 30. Even though it's not necessarily optimal with very small sample sizes. What if you had a sample size of 3? Then it's really hard to do any analysis with 3 points of data. So we're going to start with a confidence interval. And confidence interval you can think of like we talked about last time with determining significantly high and low values. Is say we have a distribution. Okay, so I'm going to clean this up a little bit, and I'm going to look at just this. Say we have this distribution, and we want to estimate the mean of a sample. We want to estimate it, okay? Well, the way we can estimate it, or we want to estimate the mean of a population, rather. We want to estimate a population mean using a sample mean, right? If I take a sample of, the height, I'll use this example again, the height of all Fontbonne students, and I take a sample of 20 students, well, with 20 students, I can't determine the overall mean for the entire school population, right? It's only a sample. But maybe from that sample, I can make some inferences. Or I can determine a range. And that range is your confidence interval. So say we wanted to talk about a 90% confidence interval. Well, what that's asking is, okay, if I want to make a distribution to describe this population mean from this sample, then in this t-distribution, I need to find, what two numbers, we'll call them A and B, what two numbers A and B, so that this is 90%, right? We saw how to do that in the normal distribution. But now we're working with t-distribution, so it's a little bit different because we're working with a sample, and this interval, this entire distribution will change shape depending on the sample size. And because that's always changing shape depending on the sample size, then changing the sample size changes what these numbers will be. So the sample size does matter in this. Okay. And there are a bunch of formulas and stuff you could do to compute this, but we are going to end up using software. And how the formula typically, or how the formula goes, is in a t-distribution, you take your mean, and then you add and subtract some number. I call it t star, times your standard deviation over the square root of your sample size. And this will depend on your level of confidence. It'll depend on your sample size. And again, back before software was very popular, people used tables and such to figure this out. So in R, we can do this without much difficulty. To do this, we're going to create our data. I'm calling it X, right? And it's just this list of numbers. So our examples listed below are weight in hectograms of randomly selected girls at birth. Use a sample to construct a 95% confidence interval for the mean birth weight of girls. This is the type of weight of girls. So we create our data. I'm calling it X. So whenever I refer to X, it's referring to all of these numbers. And to do this, a confidence interval, we use the command t.test. And we're going to see this command later too, but we can use it here. T.test, we feed it our data, and then you specify your confidence level. So this problem asks for a 95% confidence level. So we're setting our confidence level to 95%. So if you wanted to change the confidence level, you could just change this 95 to 0.90, 0.99 if you want it different. And if you ran just the highlighted part without this $ conf.int, and you ran that, it'll give you a lot more information than you want. It will give you the confidence interval, but it'll give you that with a bunch of other information. So adding on this $ conf.int says we specifically want to get the confidence interval out of this. So my confidence interval here, I click run on that, is this. So my confidence interval is 29.24, I'll go 3 decimals, 7 to 32.486. What this says is that we are 95% confident that the true mean falls between these two numbers, 29.25 and 32.49, based on our sample. Another way you can think of it is if we did repeated samples. If we took a sample of this size over and over and over again, a random sample over and over and over again, what this also says is that 95% of the time when we do those samples, our mean is going to fall in between these two values of that sample, is another way you can interpret it. And changing your confidence level will change the width of your confidence interval. So if we lower it to 90, we can see that the confidence interval is narrower, right? Because we change it to 90, right? This was 95. If we change it to 90, we get 29.537, 32.197, right? And this is a narrower interval than this one, right? The bottom is bigger and the upper number, the higher number of the interval is smaller. So it is a narrower interval. And similarly, if you increase your confidence level to 99, it's going to be even wider, right? If you increase your confidence, you're going to increase the width of your confidence interval, right? Because if you want to be more confident, then just give more numbers, right? If there's a wider range of numbers, then it's more likely than the mean falls within that range. So 28.619, 33.114. The extreme case would be, what if you want it to be 100% confident? Well, the only way to be 100% confident is if your interval is negative infinity to positive infinity. So if we changed this number, this 99 to 100, well, or that would be just 1. We are 100% confident that the true mean is between negative infinity and infinity, right? Now that's the only way we could be 100% confident. This is the only range we could give to be 100% confident. So you never see a 100% confidence interval because it's always negative infinity to infinity. Okay. Let's do another one. Listed below are the amount of arsenic levels in samples of brown rice from California. The data comes from the FDA. Use a 90% confidence interval. So we want to see if there are arsenic levels here. The FDA measured arsenic levels from brown rice from Arkansas. Can the confidence interval be used to describe arsenic levels in Arkansas? So we have these different states in the U.S., California and Arkansas, and we're looking at arsenic levels in samples of brown rice, right? If there's too much arsenic in the rice, then the rice is not healthy to eat and people will get sick. And we want to avoid that. So we're going to create the data. And again, t.test, enter your data, specify your confidence level, and say you want the confidence interval. And we get a confidence interval of 5.00. I'll do 2 decimals to 7. That would be 70, rounding it to 2 decimals. So we are 90% confident that the true mean arsenic level is between 5.00 micrograms and 7.70 micrograms. And then it asks this question is, can it be used to describe arsenic levels in Arkansas, a different state? And the answer is no, right? Because the sample comes from California. A sample in California has nothing to do with Arkansas, so this range cannot be used. So this is saying that we estimate that the average amount of arsenic levels is between 5.00 and 7.00 micrograms. So what would happen is the FDA, I believe this is Federal Drug Administration, has its own benchmarks, its own thresholds for what is an unhealthy amount of arsenic levels. And if that level is within this range, then we would say that the brown rice is not healthy to eat, and there'd be a lot of health concerns regarding that. Okay. And then next, building off of a t confidence interval, comes a t-test. And what this is for is this is testing the claim about a population. a population mean. Okay. And whenever you test a claim, you always have a set of hypotheses. If you've ever had some kind of science class, you make your hypothesis, you run an experiment, and you see how the results relate to your initial hypothesis. So we make two hypotheses whenever we do a test. One is called a null hypothesis. And is denoted HO. And then you have an alternative hypothesis. Which is typically denoted as HA. Your null hypothesis is a statement about both of these are statements about the mean. And how the null hypothesis is, it's always that the mean equals some number. Right, and the problem will tell you what that number is. And your alternative hypothesis is always something that is the mean is bigger than that number, the mean is less than that number, or the mean is not equal to that number. And you'll be able to tell from the problem how to decide which one of these three it is. So, for example, the problem we're looking at is the summary of body temperature statistics on a certain day is as follows. Okay, it tells us the sample size, the mean, so it tells us the sample size. It tells us the mean. It tells us the standard deviation. And it gives us a significance level. We'll talk about that. That's usually abbreviated with the Greek letter alpha. 0.05. And we want to test the belief that the population mean is less than 98.6. So our null hypothesis for this problem is that the mean is 98.6 degrees Fahrenheit. And your alternative hypothesis, right, your mean is always going to be the number they're referring to here. We want to see if the mean is less than 98.6. So your alternative is that the mean is less than 98.6. Okay. In a t-test, this number and this number will always match each other. These will always be the same number. It's just your null hypothesis is always an equal statement. Your alternative hypothesis is some not equal statement, whether it's greater than, less than, or not equal to. But these numbers will always match. These will always be the same as each other. Okay. And we want to calculate a t-test statistic. And remember, like we did in the normal distribution used a z as its test statistic, and the way that worked was it was your value minus the mean divided by the standard deviation, and the t-test statistic is similar. So it is equal to your sample mean minus the mean in your null hypothesis divided by your sample standard deviation divided by the square root of your sample size. So if we work that out in this problem, this would be my x bar is 98.2 minus 98.6 divided by your standard deviation 0.62. That tells you that here. And then divided by a square root of 106. So those are some ingredients that we need, and let's see what this turns out to be. So I'm going to enter all the information here. So when you do your own problems, you can just change all of these numbers according to what you need. So X I'm using as my population, or as my sample mean, mu as my population mean in the null hypothesis, S for my standard deviation, and then 106 as n for the sample size. Okay. And then this is that formula that I wrote out here. X minus the mean divided by your standard deviation over the square root of your sample size. And that number turns out to be hold on. Oh, there was an error. Okay, I forgot to comment this out, so it ran that and it didn't know what to do. Okay, so let's clear this. Let me rerun all of this. There we go. Okay, so my t in this problem is negative 6.642. Okay, and what we're doing here is, if we have a t distribution, say it looks like that, and here's the mean, 98.2. Well, not 98.2, but rather 98.6. Right? This is the initial assumption. We're assuming that the distribution has this mean, is what the null hypothesis is. It's our initial assumption about the population mean. So we're assuming that it's centered at 98.6. Our sample mean was 98.2. Okay, so 98.2 is somewhere over here, right? What we're doing is, since this is a less than, we're looking at everything less than 98.2. Okay. And what we want to do is we want to find this probability. We want to find this proportion. And that value is called a p-value. Right? So what this p-value is it's the probability that we are less than 98.2, assuming that the distribution has a mean of 98.6. Right? So to calculate a p-value, we will do that in R. So a p-value, remember, it's a probability. This is the probability that our sample mean is 98.2 or less, because it's whatever your alternative hypothesis specifies, assuming that the real population mean is 98.6, right? And that's where that null hypothesis comes in. So we're finding this p-value. So if we calculate this p-value, we can do that in R. We're going to use pt to calculate a p-value. P for p-value, or probability, and t for the fact that we're using a t distribution. Okay, right? We saw before with the normal distribution, we used p norm for the normal distribution, p binom for binomial distribution, now pt for t distribution. Okay, we give it the t value, which we already have saved from the line above, so you don't need to change that. And then another thing you put in is n minus 1 is a parameter that gets fed into this, your sample size minus 1. And this is called your degrees of freedom that you see. You'll see it as df, which is degrees of freedom. And in this problem, it's 1 less than your sample size. What degrees of freedom measures is, say I had a sample size of size 4, okay, and these were the 4 observations, A, B, C, D. what I want to do, what degrees of freedom you can think of, is what is the most number of guesses I need to make to figure out, so which one of these sample elements you are. So say I have 4 subjects in front of me and each of them are labeled A, B, C, or D. Okay, what is the most number of guesses I need to make to determine which observation a person is, right? So say I'm talking to person, we'll do the extreme case. Say I'm talking to person D and I don't know it, okay? Well, I can ask, are you person A? And they would say no. So I've used one guess. And I say, okay, are you person B? And they say no. Okay, I've used 2 guesses. Then I say, okay, are you person C? And they say no. I've used 3 guesses. But I don't need to make another guess, because if I know they're not A, B, or C, I know for a fact they are person D. So I only needed to make 3 guesses. So notice that was 1 less than the sample size. So your degrees of freedom in this little scenario I made is 3. It took me at most 3 guesses. Say I was talking to person, instead of person D, say I was talking to person B. And I asked, okay, are you person A? And they say no. I say, are you person B? They say yes. Right? So that took me 2 guesses, but the most that it will ever take is 3. 1 less than your sample size. And that's your degrees of freedom. And that's what affects your distribution. Remember, before your distribution, it could have been semi-differently shaped depending on your sample size, and that's what that controls. So your degrees of freedom in this problem is 1 less than your sample size, which is why we have this n-1 here. And this will give us our p-value. And this gives us a weird-looking number. So it says here, let me clean some of this up. Okay. So it tells me my p-value is 7.018. And then it says E minus 10. What does that mean? So in R, this is its way of talking about scientific notation. Scientific notation meaning that means times 10 to the minus 10. So what this means is really you're moving the decimal to the left 10 spots. So this is really 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. This is your p-value, and it's very, 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 very small, right? So this is a very small probability. It's essentially 0. And what you compare that probability to is your significance level, okay? So if your p-value is less than alpha, you reject your null hypothesis. If your p-value is bigger than your significance level, you fail to reject. You don't accept, you fail to reject. Okay? So what this means is we're setting 0.05 as your cutoff. We're setting 5% as a cutoff. So what that means is if the probability is less than 5%, right? If the probability is less than 5%, this value, then we are going to reject the null hypothesis. We're saying that if there's less than a 5% chance, if there's a less than a 5% chance of the mean being less than 98.2, assuming the population mean is 98.6, less than 5%. That means that's so unlikely to happen by random chance that we don't actually think this initial claim is true. There's less than a 5% chance of this happening by random chance. That's so low. So low for it to happen by random chance that we think this is not a true statement. this is the probability here. This is the probability that we get a mean of 98.2 from a sample of size 106, assuming that the true population mean is 98.6, right? That was the assumption we made. So it's essentially a 0% probability. So it's a 0% chance that we're going to get this, assuming this is the mean. So this must not be the mean. This mean must be something else, is the conclusion. So the way we conclude these problems is it's written out here. Since the p-value, which is very, very small, is less than your significance level, your alpha level, we reject the null hypothesis. The probability is so small, it's basically 0. So this must not be, this value here must not be the population mean, is what this says. This value must not be the true population mean. Evidence suggests the true mean body temperature is less than a 98.6. So if you wanted to increase this proportion here, you would have to shift this over to the left. You would have to shift the entire distribution to increase that. So evidence suggests the true mean body temperature is less than 98.6, which is your alternative hypothesis. Okay, this shouldn't be is not, is less than. So you reject the null in favor of the alternative here. So your evidence suggests that the true mean is less than 98.6 is the conclusion here. Okay. Let's go through another one. Let me comment this out because I had that issue before. I'll clear this. The summary of earthquake statistics is, we're told the sample size is 600. We're doing this new example. We're told the sample size is 600. The mean is 5.82. And the standard deviation is 4.93. And we want to use a 0.01 significance level. Okay. To test the belief that the population mean is more than 500. Okay. So the population mean is more than 500. Or not 500, 5.00. kilometers. So your null hypothesis is that the mean is 5.00 kilometers. Your alternative hypothesis, notice this is a greater than statement. We test the belief that it is more than, so that your mean is more than 500, or I keep saying 500, 5 kilometers. Okay. So we have all these parameters. And to give you a visual again, we have the distribution here centered at 5 kilometers, and our sample mean is this 5.82, and what we care about is finding this probability here, the probability that it is more than 5. Okay, so this is all the same except for one detail, right? So our t-test statistic in this problem is 4.074. Before, we found this proportion, which was off to the left. By default, remember this probability gives you the lower tail. If I want the opposite, if I want this end, I need to do 1 minus, because R by default will give you the probability that it's less than, it'll give you this. And we want the opposite, which is why we have the 1 minus here. So your p-value is, if I wrote that out, remember this means 2.619 times, this is our p-value, 10 to the minus 5, which is 0.00002619. So the p-value, you compare that to your alpha level, your significance level, and this p-value is less than the significance level. So remember what this means. This is the probability that with random sample we get 5.82 sample mean with a sample of size 600, a very large sample, assuming the population mean is really 5 kilometers. This is so unlikely. This probability here is so low. So what we'd say is, since the p-value is less than the significance level, we reject the null hypothesis. Evidence suggests the mean earthquake depth is more than 5 kilometers. We reject the null in favor of the alternative here. Now, these are problems where you were told all of this information, the mean, the population mean, the sample standard deviation, the sample size. What if you weren't given all that? What if you were just given all of the data? So an author obtained times of sleep of randomly selected adult subjects included in the National Health Nutrition Examination Study, and those times measured in hours are listed below. A common recommendation is that adults should sleep between 7 and 9 hours. Use the p-value method with 0.05 significance level to test the claim that the amount of sleep is less than 7 hours. So this is what we're looking at. So in this example, our null hypothesis is that the mean is 7 hours, and your alternative is that the mean is less than 7 hours. And in R, it's actually almost easier being set up this way with just given the data. And how this will work in the textbook is, in the textbook you're going to be given a list of numbers or table or something, and I just have them typed out here. So we create our data. I'm calling it times. I'm actually going to clear this to start fresh. And we come back to this t.test command. All right. We give it our data, and now you have to specify your alternative hypothesis. Our alternative hypothesis is a less than statement. So alternative equals, and then you specify less. And then you specify the mean in your null hypothesis. And if you leave it just like this, you'll get a lot more information than you want. You can just specify you want just the p-value with the $ p-value. But this is how it's formatted. T.test is it's the same that we used in the confidence intervals. You give it the data, and we're not making a confidence interval to specify the confidence level. Instead, we're doing a hypothesis test. So we specify the alternative hypothesis as a less than statement, and if it was a greater than, it would be greater here, and you specify the mean in your null hypothesis here, 7, and then the p-value. Here we get a p-value of 0.3886, or 887 rather. So what this means is the probability that we took a random sample and received these results, and we can see all the results if you wanted. If you wanted to remove this p-value, it tells you the t is negative 0.28977, and it tells you the sample mean. So if you were to draw this out, it would look like this, where the mean is 7, the sample mean is 6.83, and we're looking at less than. What it's saying is that this probability this area under the curve is 0.3887, okay? Which, if you think about it in percentages, that's 38.87%. So there's a 38.87% that we get this result, assuming the real mean is 7. And 38.8 is not that unusual, right? That's more than a third of the time. The other percentages we got were very, very small, but this is large, and it's much larger. Our p-value here is bigger than our significance level alpha. We were told to use 0.05 significance level. And if you're never not told a significance level, you assume it's 0.05. It'll usually tell you to use 0.05, 0.01, 0.1, 0.025. If it doesn't tell you, though, you assume 0.05 as a general rule to follow. So since your p-value is greater than the alpha level, we fail to reject the null hypothesis. We do not have sufficient evidence to suggest that the mean amount of sleep is less than 7 hours. We do not have evidence to refute the null hypothesis. We do not have evidence to refute the null hypothesis. We do not have evidence. We do not have evidence to suggest the alternative hypothesis. We're not saying this is the mean. We're just saying that our current data and evidence is not telling us otherwise. Okay. And now we have an example where we're going to pull in a data set. So this is going to come from the bacteria example data set that we can read in. I'm going to go ahead and run that, and a window is going to pop up where you can pick your data set. And now it is now in there. So we have all this data here. So Ohio considers it unsafe if a 100 milliliter sample of water contains more than 400 coliform bacteria. The fecal coliform levels at 20 Ohio parks were sampled, and that's what is in this data. Are these data good evidence that on average fecal coliform are unsafe? Remember what unsafe means here. Unsafe means more than 400 of this bacteria. So your null hypothesis in this example, we're looking at 400 as a reference. Your null hypothesis is that the mean is 400. 400 coliform bacteria. Your alternative is that it's unsafe. Unsafe meaning more than 400. So we have the data. And we can use the command t.test again, give it the data. This data only has one column, so you don't need to use a $sign to specify anything. The alternative hypothesis is a greater than statement. Your null hypothesis specifies the mean is equal to 400. And we get a p-value of 0.00099. I'll leave it at that. This p-value, here's our pattern. We compare that to the significance level. Okay. And this problem did not give you a significance level. So you're going to assume it's 0.05. Our p-value is less than your significance level. Since the p-value is less than the significance level, we reject the null hypothesis. Evidence suggests that the water is unsafe. And if people are swimming in, right, this is from Ohio State in the U.S., Ohio State Park swimming area, and there's an unhealthy level of bacteria, then they need to close the swimming area and treat the bacteria before allowing people to swim. And again, if you wanted more information, more than just the p-value, you can certainly leave this part off and you'll get a lot more information. We can also use a t-test to compare two groups. So this is a two-sample t-test. Do women and men differ in how they perceive their life expectancy? A researcher asked a sample of men and women to indicate their life expectancy. This was compared with values from actuarial tables, and the relative percent difference was computed. Perceived life expectancy minus life expectancy, and then divided by life expectancy, and then converted to a percent. The data can be found in the life expectancy CSV file. So let's read that in. I'll clear this. Okay. And we have the life expectancy data set that we can read in. So this data has male and female, and then these life expectancy percentages. So this is saying this person, their expected was 28% below what it actually is. This female, what she thought her life expectancy was 20% below what it actually is, according to actuarial tables, and so on and so on. And notice that these aren't all the same sample size, right? The male is a sample size of 6, female has sample size of 7, so the sample sizes don't have to be the same here. And now we're going to talk about the null and alternative hypotheses. So we are comparing these two groups. Your null hypothesis, how you would think is that the mean for males is equal to the mean for females. Right? Because if they weren't equal already, then you don't have to run the test if you didn't assume that. What we're looking at, though, is how we interpret this is the same as saying the mean for male minus the mean for female is 0. And when you're doing a two-sample test, this is the population mean you're talking about. You're talking about the difference between the group. You're going to assume there is no difference between the two groups in a two-sample test. So the null hypothesis is that there is no difference. The mean is 0. The mean, which represents the difference between the two groups, is 0. And we want to see if do they differ. It doesn't say one has a higher expectancy than the other. It just says, are they different? So different will be a not equal to statement here. Okay. So in tests before, we had to specify if it was a greater than or less than statement. But if it's a just different than, it could be greater than or less than, you don't have to specify. By default, it's going to assume not equal to by default. If it's something like less than or greater than, then you need to specify it in the command. But if it's not a greater than or less than statement and it's just a not equal to statement, that's what R is going to assume by default. And you don't have to enter it. So we can do t.test, and it gives you the mean of the two groups. You could also use $p-value like we have been to just get the p-value. And our p-value here is 0.05281. And your significance level, did they tell us in the problem? It looks like they did not. So you're going to assume 0.05. And this p-value is really close. It's technically bigger. So since the p-value is greater than, we fail to reject the null hypothesis. We do not have evidence to suggest that the mean perceived life expectancy of men and women differ. But this p-value is very close. It's kind of on the edge. So what you would generally say if you're doing this as a practitioner is, since the p-value is really close, if it's a little bit above or a little bit below, you might want to run the experiment one more time, regather data, and test once more to see if it's still on the higher side or if it goes below, and just double check your results with redoing the experiment if you have the available time, money, and resources to do the experiment again. Next one, and I believe this is our last one. Researchers looked at the effect of lemon, a stimulating odor, on customer behavior in a small restaurant. The data can be found in the odors CSV file. Do the data suggest lemon odor decreases the amount of time customers stay at a restaurant? So it's not just does it change the amount of time, but does it decrease the amount of time? So our null hypothesis for these problems is always going to be the mean is 0, meaning there's no difference. There's no difference between time customers stay in the restaurant with lemon smell and without. So we're doing time with lemon. So this represents mean with lemon minus mean with, I'll say, no lemon. Okay. Or I'll just use Y and N for yes, no. Yes lemon, no lemon. Okay. So our alternative hypothesis is we want to see if the time decreases, meaning the time with lemon is smaller than without lemon, right? So what this means is if this is smaller than this, then this minus this is going to be less than 0. Just to show that, again, we want to see if the time with lemon is less than the time without lemon, right? So if I subtract this from both sides, I get mu y minus mu n is less than 0, but this is how I defined the population mean. So this is saying your alternative hypothesis is that the mean is less than 0. So your alternative hypothesis here is that mean is less than 0. So we're going to read in the data set, okay, and the odor file. Let me clear this. And we can see what this data looks like. No odor and odor. Okay, and all these values, again, they're not necessarily the same sample size. No odor has 2 more observations than with odor, and that's okay here. We're going to run the t-test. T.test, there's 2 columns here, so you need to specify which column you want to talk about. MD $odor and MD $no odor. The order you put these in does matter because I'm talking about, I have this defined as, right, this is mean of odor minus the mean of no odor, right? So I'm putting odor first and no odor second. And I'm going to specify the alternative that it is a less than statement and getting the p-value. If you wanted to change these, if you wanted to do no odor first and odor second, you can, but then you'd have to reverse this to not less but greater. And you'd get the same p-value. P-value of 0.356056. I'm just going to change this back to the original. So Were we given an alpha level here? I don't believe so, so we're going to assume 0.05. Since the p-value is greater than alpha level of 0.05, we fail to reject, right? We fail to reject the null hypothesis. We do not have evidence to suggest that lemon odor decreases the amount of time customers stay at a restaurant. And this would be interesting to know, because what if the p-value was really small? That would mean the odor does matter, right? Which can benefit the restaurant, because then the restaurant can leave out lemons to have a lemon scent to get people to stay in their restaurant for less time. And if customers get up from the restaurant in less time, then they can seat new customers faster and make more money. Right? So if the results were significant, they're not here, but if they were, then this could be a valuable business decision for the restaurant. They could get people out the door faster to seat more people more frequently, and in turn make more money, increase sales. Okay. So with this, you are able to do the next homework 5. Please let me know if you have any questions on any of this material or any of the homework problems.